Hello, everyone. Welcome to another meeting of our conversational reading group. Today, we are very excited to have Tatiana from Apple talking about a very hot and I think very relevant topic to these days, low latency conversational agent. As always, if you have any question during the talk, please raise your hand or drop them in the chat. Without any further delay, the stage is all yours.
Thank you. First of all, thank you so much for inviting me and giving the opportunity to speak about our work. And yeah, I'm happy to answer any questions. And if you have more questions, feel free to mail me after the talk. Okay, so with that, yeah, I'm going to talk about low latency conversational agent, the work which we're doing over the past year in our team. And this work cannot be, done without amazing people which work with me over this year. Okay, so yeah, I'm just at SRU today, still in Hawaii, and in that sense, we discuss many different problems about the AI agent design, and I would say this is not solved yet. It's very open problem. And as you know, like long time ago, we built different components on speech recognition, speech generation, language modeling, and the classical thing which you may imagine, how to design the conversational agent nowadays, for example, is just stack these pieces together and make it work. So what is good about this particular system is interpretability, because every component here has a clear notion what it's doing, and you can observe is it wrong or correct. Language understanding, this is known for a long time, and currently people also benchmarked some stacking system, for example, just taking the Whisper and then some popular language model and check how it's working, and it seems working very well. The main issues with cascaded system, which I often hear in all presentation, and I saw a lot in the SRU, and also you can find in the paper's introduction, that cascaded systems are bad because they have error propagation. Every system is making mistakes, and then you accumulate these mistakes over the pipeline. The second problem is the low latency. That this system actually don't have low latency, so they are very slow, because you need to wait every component to finish their processing before next component can continue. And I think the critical thing we can add to this list also emergent capabilities. So why we like all these LLMs, because just train for the next token prediction, and then suddenly we can do a lot of in-context learning task. But in terms of cascaded models, we really cannot have that for the speech processing or for the audio processing in general. So what happened in past couple of years after LLM appears, of course, people started to go, okay, let's now build end-to-end models for speech processing and or for the audio processing, and combine maybe even audio, music, and speech together, because like we believe that this end-to-end training will solve all our problems. But interesting that in recent publications, and I added recent one from the new RIPS, highly recommend to check it, from Google people. And another one I added also, that this was appeared in iClear, Dynamic Superb Phase 2. I guess some of you know about these things and maybe participated in that. So if you benchmark really for some tasks, the end-to-end models which we currently have and cascaded system, you will observe the following. So language understanding actually is the best in cascaded models. So we lose capabilities of the basic things which we believe it should be in end-to-end system, right? But we don't get much using the additional prosody information. So it's really far away from the main baseline which we have right now. Interpretability, that's becoming harder in this system. And also you can imagine how many people working on hallucinations in LLMs and all the issues and safeguarding for them. This all problems we're going to have. People were discussing this at SRU also, and there is no solution right now, of course, and there will be some specifics related to speech itself. Error propagation, you believe that end-to-end should solve it, but why we're still behind in language understanding. Maybe we're still doing error propagation. Maybe now it's just behaving in a weird way, and we just don't know about it. So it's under question for me, to be honest. We don't have confirmation, from the hypothesis testing that it's really not happening. Low latency. Everyone is saying that a speech LLM is going to be low latent, but with a low latency. But do we actually have these benchmarks? Do we actually confirm that? And then you can imagine now people actually publishing the papers on streaming tokenization, because all tokenization for speech LLMs were full context, and this is not really, low latency. Emergent capabilities, that was under question, but I think a month ago, there was appeared the paper from Xiaomi where they're showing that they improved 5-shot in context capabilities. It seems started to work, but I think we can say, thumbs up, but more and more things need to be done here and investigated and benchmarked. So it's kind of happening, but we'll see where it's going. Okay. So in that sense, we can say, okay, end-to-end worth exploring, but we have many, many things to do before it's going to beat really cascaded, very well-established baseline over which we built over the many, many years. Okay, so that's why what we did, we actually started to think, okay, we need to start, all research from the baseline. What is the baseline cascaded model? So let's build a strong cascaded model. And one of the critical issues which we can solve is low latency. Like error propagation, for me, it's under question. We need to have good benchmarks really to test that. So Google dataset and dynamic superb from many, many people, that's potentially very good things where we can start. But yeah, the question, what downstream application you actually care about. So low latency, it seems like let's look into that and think about, is it really the problem or not the problem in cascaded system, and have the strong baseline, which we can really, test for many other features. So in that sense, yeah, you just train speech recognition, large language model, TTS, and vocoder, and try to optimize the whole system to make it usable, kind of even for researcher, to explore what's happening. So we focused on low latency as a first principle for design. I believe, my personal opinion, the system should be user-centric and maybe not full duplex. We can, discuss that kind of research question. So we designed it to be user-centric. Interruption capability, that, in my opinion, what was missing in the past systems. If you know any other system, please let me know. But we redesigned a bit the interruption pipeline in our system. And the key points for me also in the design of the system was, and for some of my colleagues, it's privacy of the system and ability to run on device. And some people may care about, situations where you don't have internet connection and you wanted to run this even without any, connection to the external world. So that's why we focused how to make it work on device. Okay, so this is our demo, so please listen.
Can you tell me the names of all 8 planets in the solar system?
Sure. Here are the names of the 8 planets in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Is there anything else you would like to know?
Huh, that is strange. Why isn't Pluto considered a planet?
Pluto was reclassified as a dwarf planet by the International Astronomical Union in 2006 because it does not meet all 3 of the criteria used to define full-fledged planets. Would you like to learn more about this topic?
Yes, I would. Could you give me a more detailed description of why they made that decision?
Sure. In order for an object to be considered a planet, it must meet 3 criteria. It must orbit the sun. It must have enough mass for its own
No,
gravity
this
to...
is boring. Can you actually tell me a joke about Pluto?
Here's a joke about Pluto. Why did Pluto break up with Uranus? Because it thought it was a little too far away from the sun. Do you have any other questions or topics you would like to discuss?
Yeah, that's pretty funny. Could you give me a story about Pluto?
Sure. Here's a story about Pluto. Once upon a time, Pluto was feeling left out because it wasn't considered a real planet anymore. But then it realized that being a dwarf planet was actually pretty cool, and it lived happily ever after. Is there anything else you would like to talk about?
Oh, that's nice. Thank you for speaking with me.
You're welcome. It was nice talking to you. Have a great day.
Okay, the problem that I need to switch my mic back and forth. When I'm playing with the audio, I cannot talk. Okay, I hope you heard it all, right, Pune?
Yeah.
Yeah.
Okay, perfect. Okay, now you hear me too. That's good. Okay, so hopefully you saw here, I come back a little bit, but this is our, so the main thing is kind of, framework itself to show you the whole system. So we have the gradient which people often use, and you see here that we observe the latency of every component. We have speaker ID right now is not integrated, into like conditioning whatsoever, but just for observability that our speaker ID system is working properly, and it was showcasing to you. And then, you saw conversation. So we're putting all the text also for you to see what's going on with the system and how the eyes are working, what the language model actually generating, and if TTS, correctly pronouncing the things. And then you see additional states for the assistant and for the user in terms of motivation and emotion. I will go in deeper how we did this, and kind of you observe the whole conversation. Okay, so with that, let's go inside what we did actually. So we kind of worked on every piece of the system over this like year or two, and one work was on the speaker recognition. So if you want to know more, here the QR code to the paper. So this is the fully unsupervised model that we pushed and tried to get the sort of speaker recognition on the diverse data, and was led by Zach. So then on the speech recognition side, we pushed towards the mixture of experts. This was presented at the SRU, so that you can outperform, for example, Whisper Small on the conversational data with 2x less active parameters. So mainly kind of increase the model size to get better model, of course, but then at the inference time you have less number of active parameters, so that your inference will be faster. So on the language model side, the user emotion and user motivation, what you saw, and also for assistant, this was kind of augment the LLM capabilities with emotion-oriented like additional states, which we predict before generating the full response. On the speech generation, we first started from tokenization. Maybe you heard about our DML discretized version of the spectrogram. We built the decoder-based TTS first with the full context, and then we switched to the streaming version and did the speak stream with the final like state-of-the-art latency, 50 millisecond on M4. So this is on device. This is not on, NVIDIA GPU, which people often benchmark. And then we also found that the bottleneck in the end becomes vocoder, because vocoder needs a full kind of 10 frames, for example, to start the generation of the full wave chunk. So that's why we started to look into streaming vocoder, and this is part of the speak stream paper. It's some frame rate, it's really very good, but for some frame rate we need still improvement. So a bit work in progress, continuing working on streaming vocoder. Okay, so with that, let me go deeper into every piece of the work, and then I'm going to cover chip chat itself, how it's working in terms of the framework and interruption handling. But we need to go deeper into the models themselves, because that's kind of answers how we get the low latency. Okay, for speaker work, what we did is the following. So you have the speech signal, you have the neural network, you have the loss function, like supervised or unsupervised. But main thing what like people do now is in training phase you mask, and then you predict mask things, so like bird training for unsupervised methods. But at the inference time, of course, you don't mask, and you get the speaker embedding. And what we do, likely most of you know, right? So we use it either out of the box, or we do we can do bootstrapping of the iterative self-training in our case for retraining the next model. And in practice, what you do, you compute the cosine similarity, and you decide with threshold if it's new speaker or kind of the same speaker. Okay, so main thing what people were doing, they were trying to find this kind of bootstrapping mechanism from which model you can start. And the baseline models, they kind of re-implemented the Dino from speech community for speech recognition kind of design from the first principles, but applying this to the speaker model. And then what you do is as soon as you have the model, then you generate new embedded vectors, and then you reiterate from that training to improve further your model. So this kind of self-training pipeline we had a long time ago in speech. I was like a long time working on that. But the same thing people started to apply also in speaker. And the main crucial thing was how to get this initial model. So the main question we asked is, do we need really this strong model to bootstrap? And can we use actually simplified, model, very weak model, I-vectors, which is fully unsupervised and doesn't need a lot of tricks to train this initial strong model like in Dino. Dino is not really, super trivial to train. It can collapse and many other issues and tricks you need to do on the engineering side for the training itself. So eventually we just replaced in this kind of self-training pipeline the initial embedding with the initial model with I-vectors, similar to the Hubert, where people use MFCC, right, to bootstrap the whole unsupervised model for kind of foundational model. And we did experiments on VoxyLab too, which often people do. We used a couple of the encoders, but also the one which currently kind of used by people for SOTA models, MFA conformer. And then we added some additional augmentations during the training, which is standard also, which people do. And what is interesting, in the end, we get a competitive model. It's very close to the SOTA models, and it's very simple to train because I-vectors is very known simple technique. We did some additional ablations inside the paper on different augmentations, on different clustering, on how many actually self-training steps you can do, and where you saturate. So if you want to know more details, go to the paper. But yeah, outcome in that I-vectors are good starting point, and you don't need really strong teacher. And we see over the testing demo during the ASRU with very different people, it seems working pretty stable. Okay, now moving to speech recognition. So as I mentioned before, we did the mixture of expert for ISR, also presented at SRU by Zijin. And the key point is if you apply the switch transformer, which is very strong baseline and used in many places, including language modeling, you will see that actually for the speech there is no structured use of experts across the layers and across the time. And it seems like experts don't do really very good specialization or cooperation for speech. So what we thought is let's do some inductive bias and encourage this coordination and strong specialization and getting some structured patterns along the speech. And here on the bottom plot you see that now the same like experts marked as with different color, and you see now you have the structure across the time and across the depth of the network. So main idea is very simple. It's very straightforward to implement, so you can just go and implement right away in your in your pipelines. So what we proposed is to share the rotor parameters. Okay, be very cautious here. It's not sharing the decisions, it's sharing the parameters, which means that depending on the input you're going to have with the same shared parameters, maybe different predictions. So this does not guarantee that all the layers will give you exactly the same expert prediction. But what we see that it's actually giving structured predictions. So the group of layers navigating to the same expert And with that, we improved the accuracy. We saw that for conversational data, for some reason, we see some instability and collapsing for switch transformer, the performance becoming really worse sometimes. But with OmniRotor, in the end, we see that training stabilized. We don't have the answer for that. We have a hypothesis, but I think more experiments needed. So yeah, the method itself, simple, straightforward. So no embedding networks, which people propose in prior works. There are some different losses to make it stable and to make it better. We don't use that too. Kind of no other inductive biases, for the optimization itself. So you're using some architecture inductive bias, but not other things. Okay, so with that, we did experiments in the paper on like what we call speech crowd data set. So we collect large-scale conversational audio from publicly available sources. Of course, all data unlabeled, so that's why we generate pseudo labels with the Whisper pipeline. Important thing here, of course, filtering unreliable pseudo labels. Otherwise, your data will be too noisy. And we, in the end, retain approximately 1 million hours of English speech segments for the training, and we train our models on this data to have kind of, diverse set of the experiments. So the baselines we used is dense and switch vanilla transformer model, and all models we trained with CTC, simple CTC laws. So yeah, in the end, we see that OmniRotor outperforms switch transformer, and of course, it outperforms the dense model, but with the same number of active parameters. So if we compare, for example, with the Whisper small model of similar size, which we had, so in this case, we get parity or even outperforming on some conversational data, the model. In the paper, we have a bit bigger models, and in the demo, which I showed you, this was 600 million parameter model with around 150 million active parameters because we used 4 experts. Okay, so we also did application on different number of experts, different model sizes, as I mentioned. So we see that it's improving over switch transformer recipe, like along all these experiments on different data sets. We looked into the, do we really improve now a specialization? And what we did is we randomly permute expert assignments for each token and varying probability with which we, permute this thing. And then we measure the word hear rate. And the main important thing here, if experts are very specialized and, tied together, you're going to see higher degradation in word hear rate. And that's exactly what we saw. So for OmniRotor, we see way higher degradation with increasing the probability of the permutation compared to the switch transformer. We also looked into, how the adjacent layers correlated, so that kind of confirmed some cooperation between the experts, between the layers. And here we also see across the different pairs, early layers, of course, do not cooperate much because likely they perform, low-level feature extraction. But later layers, especially the last ones, they do very good, correlation in their decisions and choices. Yeah, we looked also in the, entropy distribution for the most frequent tokens, and kind of seeing that how this entropy changes, also showcasing kind of better specialization between the different layers. So more details in the paper, but just main concept for you. Okay, so now we have ISR model. So now we have transcription. What do we do with us? So for this, of course, you can now plug in just any LLM you like technically, and just be sure that it's runnable on device. But for the dialogue, our thoughts was about that, we have problem-oriented agents, but do we have emotion-oriented agents? And some works and some, places like P or Grok, they're trying to look into that. Maybe many other works, which I'm not aware of. But yeah, the main key point is kind of, augment our agent with both capabilities on, question answering, but also having some empathetic behavior. And to achieve that, the idea is inducing some latent variables which represent long-term conversational information, which can encapsulate emotions and state of the dialogue and are of discrete nature so that we can simply predict them with autoregressive models. And with that, what we did is the following. So we took the Reddit data. So this is the multi-turn dialogue data. We clean up, of course, important piece in all our reality nowadays. And then, given the whole dialogue, you use some LLM to annotate what is the motivation and emotion was for every turn. But here you have the whole, dialogue state. That's why you can have this in more precise way. Okay, so given now that you have this motivation and emotion annotation for every turn, so now you're augmenting with this additional information your dialogue in specific template format, as you can see on the middle plot. And now you're training, okay, you get this information on the middle plot, and now you augment this on the rightmost scheme. You augment with this information your turn. So now you have the user saying something, and then for the agent, you're saying that first I want to predict in specific template what is the user motivation and emotion. So kind of estimating the state in which user. Then based on that, you predict in which state should be assistant or the agent. And then based on that, you start generating the response. So this is kind of more general framework. So you can think that maybe you have very, very different states of the reality, which you wanted to introduce into your dialogue, kind of to condition, first produce them and then condition on them to produce your response. So for the training, EG, like using mixed-trail model to fine-tune with the LoRa on this specifically prepared dialogue data. And then important thing also was self-play, where you use the previous agent as a user, the new agent, as an agent, and now you do self-play of talking with each other, and then you do, of course, good best rejection selection to keep them, and then continue training with the kind of self-generated data. For the inference, you first generate latent variables, and then you generate the dialogue. So as I said before. So with that, we did comparison for different, LLM as a judge, using to see how much improvements we have. And this is comparison in terms of is dialogue became more empathetic and more kind of emotional. And you see that with this augmentation, you get significant improvements. We of course check that do you have a reduction on all LLM standard benchmarks or not after this fine tuning, and all benchmarks preserved. Plus, in addition to you have this empathetic, behavior. But the one downside is degradation on the math task, which is kind of expected, maybe. But this is what we lose. Okay, so now we have this LLM and the states which you saw during the demo. That's exactly what we generated from this LLM to have additional dialogue states, but plus condition on them to have a bit better generation for the dialogue conditions. Okay, so now the last piece is generation of the speech, right? So we need to have TTS and vocoder, and there are numerous works on the TTS, of course, and you can plug in your favorite one, but what we need is really streaming TTS. If LLM, you can plug in mostly any TTS, any LLM, because it's autoregressive and only the size of the model kind of will make a difference for the latency and on which device you're running it. But for TTS, we really need to have streaming models, so that's need to change a bit the architecture itself. Okay, so what we did, I think I can very briefly, let me just talk about tokenization, and then we go deeper into the models. So for text we have simple mapping. For speech we need to convert to some tokens, because we wanted to reuse autoregressive pipeline and just apply all LLM techniques which people did, and this is what past 2 years I think people mainly were doing. And I guess everyone knows about Mirko's and others paper and about the discrete tokens for speech generation, like surveys. So this is, I will refer you there if you wanted to vary your tokenization. Yeah, the main thing is because we wanted to use language modeling, and it's kind of the best strategy right now if you want to really train the good models. So the data, a sequence of discrete indices, and we apply the chain rule autoregressively, similar to autoregressive model. But the thing is, what we are thinking in the team is tokenization compresses the data before you know how you're going to use it. And the manifold of these compressed codes can be very curved, and it can behave in very weird ways, and you cannot really control that. So the thing, we did experiments, and in InterSpeech there was a work which did robustness check for all tokenizers or main tokenizers for speech. The issue that they are not robust. So when you train them, you're really going to go out of domain and for the weird behavior when you apply to more diverse data. So here we did experiments with, Encodec, Hubert, speech tokenizer, and Mimi. And you see that when we no noise, they kind of perform well across the board for the reconstruction. But when you go with the cases where you add some background music or you add some other person talking, some other speech as a background, you're going to see huge degradation of this tokenizer. So they are not robust to many situations, which is bad. So, okay, let me skip this because we all know that, I hope. Yeah, maybe shortly that. So that originally there was kind of split into acoustic and semantic tokens. So people were training both of them, and the pipeline of the was more complicated. Now it's simplified, and kind of the acoustic or RVQ tokens, where you have one semantic token and one kind of acoustic token, and then you train kind of end-to-end model there. The main difference between all these different, tokenizers, RVQ or Moshe or other variants of speech tokenizer, it's the question on which, information you are conditioning. So you always condition, of course, on the, because in your modeling, when you have these tokenizers, you condition, of course, on the path because it's autoregressive model, but it's important for which channels you're conditioning. So different tokenizers are different in terms of using the past information, but also using the previous channel, so that you have autoregressivity also in the channel structure itself. So in that sense, we thought, okay, this additional autoregressivity in the channels leading that you're going to lose in the latency, because you need to wait. Let's say I have 8 tokens, 8 channels in speech tokenizer of my RVQ tokens. In this case, I will need to wait 8 or 7 tokens to be generated before I can generate the next time frame. In that sense, it can pose significant latency issues. So because of these two considerations, latency, streaming property of the tokenizer itself, and also the issue being robustness, we decided, okay, let's use just MEL spectrogram itself, because this is, first of all, you have off-the-shelf decoders, which are vocoders which people developed for a long time. The second one, it's continuous in nature, and we know that this is very good feature extraction for speech processing for many years of research, right? So we can read the both semantic in there. We have all acoustic information there too. So the main thing for us is now, okay, switch from continuous to do discrete version to apply the autoregressive or machinery. And that's why we said, okay, let's discretize just MEL spectrogram. There was similar work in that sense. Let's use MEL spectra. But it's called MELE. I hope maybe some of you know about it. But they decided to stay in the continuous space. And the main issue with continuous space is that they're kind of showing this in the paper, that it's harder to train with L2 loss. You need to add additional regularizations, improve kind of or stabilize optimization process, and even a bit modify the model itself. So the model is not so simple, just transformer, plain transformer, and next token prediction. You need to do some work here to make it work. So we went this is concurrent work. We went a different route, and we went to the discrete version. Okay, so in that sense, what we do, we just have the discrete MEL spectrogram. We put into vocoder to reconstruct it back. But in terms of modeling, you just predict the discrete spectrogram. And here, important thing, we predict the channels in parallel in our modeling. And often you use 80 MEL filter banks, which will be predicted in parallel at the same time. So the main difference between all models which people did for speech based on speech tokenizer, Moshe style of tokens, etc., is exactly conditioning. So we don't condition on the previous channels for this time frame. We condition only on the past frames and predicting all channels in parallel, independently. Okay, so if you didn't see this work, so that's our title, the MEL trivial tokenization. So what you do, you have your MEL spectrogram, you just tokenize it, then you detokenize with a simple rule, and then you got this kind of spectrogram after quantization. So this is really just mathematical quantization. So why to do something like trivial? It can be computed from any raw wave, so you don't need to do any adaptation. We do not depend on any encoder, so it's applicable to multilingual data, it's applicable to noisy data. We know that spectrogram itself is very robust to the noisy conditions, and you simply can convert back with high fidelity vocoder. Okay, so the question is, first, can we do we lose anything with this discretization? So first we check in terms of the content itself. So we see that if we test on some def-clean data or test-clean data from LibreSpeech, you see that we very close to ground truth, and DML not losing much from the MEL itself. Then, of course, the question about the quality. So we tested the MOS, and we see that there is a bit degradation, but in the end, it's kind of very close to other tokenization. And the main contribution here is what vocoder you're using. So better vocoder you use, if you apply big vegan, you're going to have better reconstruction. So okay, so then I said about that spectrogram is robust. Okay, if people didn't study that before, okay, so here is confirmation again. So no noise, MEL and DML reconstruction will be very close to other tokenizers. But if you have noisy conditions with the music or other speech, you see that it's doing way better than other tokenizers. And yes, someone was pointing out to me that encoding is doing a good job. Yes, it's doing a good job. So that's one of the tokenizers which you can use. But in the past, it was shown that encodec may be not the best to use for language kind of speech language modeling. Okay, so first we also test DML with the speech recognition itself. So is discretization hurting it? And in general, no. Even sometimes a bit regularizing for sequence-to-sequence model. In CTC case, it can hurt a little bit, but the main issue is with which frame rate you're extracting the MEL and DML. Because that's the most crucial part for speech recognition to be able properly to predict the tokens. Okay, so how the model works for the embedding. So okay, let me check the time. Okay, so you have you have your channels for particular time frame. We discretize, so we get the discrete actually vector. So you have the we use exactly the same uniform bins across, the spectrogram. It's not per channel, it's global. So now you just assign the bin number for every channel where the value lies. And then what we do is we're learning embedding matrix to map now every bin to some representation. And we repeat this for every channel. And then we stack all the representations together into one big vector. Okay. And this will be our input to the model. So then you have your favorite model, whatever, conformer, branchformer, transformer model with a backbone. You get the output, you get the final vector. And now what we do, we split it back to the number of channels we had. We interpret every, piece as a representation, and then we map it back to the with the softmax to predict the distribution over the bin index. Okay, so for the now we can train the TTS model with this discretization. So let's assume that we have the text. So then we just saying that we're going to predict frame by frame the 80 channels in parallel in discretized version. So you have this kind of tokens in your text speech decoder, and we use decoder on the model in our case. Okay, so in the end, the question maybe why predict them independently? Independent channels in the end present redundant predictions. Mistakes in in one channels can be corrected by next step prediction. So that's why it's okay, and it's simpler when channels are less intertwined with each other, as we have in DML compared to the complicated tokenization. You don't know exactly dependence. And in SRU there was a work which was showing analyzing the encoded base tokenizations, and they were showing not in codec, RVQ kind of style tokens, and they were showing actually that you don't have semantic or acoustic this separation. They're actually having both information containing in them, so they are more intertwined in that sense. So with this TTS model, we showing that you can actually train good TTS model in terms of content preservation compared, let's say, to Hubert and speech tokenizer. So here, speech tokenizer is not RVQ. This is kind of parallel prediction exactly. And if we do not predict channels in parallel, then we have even like kind of worse. Okay, let's do that a bit wrong. So if we predict the channels in parallel for the speech tokenizer, we actually have way worse performance compared to the predicting the way it's supposed to be. And this actually is showing that when it's intertwined, it's harder to predict in parallel. And in that sense, DML being less correlated, less intertwined, but maybe some correlation, it's simpler to compute it. Okay. The question like which we argued over the past 2 years is that in the end people pushed a lot on the reconstruction and pushed a lot on the low bit rate, but we were arguing that actually in the modeling side we care about the frame rate, and in that case even if you have low bit rate, it doesn't mean that your model will be fast for the low latency regimes, because your frame rate is you need to predict more frames per second. That means your outer regressivity will give you like huge overhead in that case. So the question we ask then, how we can reduce further the bit rates. So nowadays you have already even not 40 frames per second, but let's say, I don't know, 6 frames per second kind of things. Back in the day we had DML with 40 frames per second, and we tried to reduce it further and see if we can go to even to faster inference. And in that sense we said, okay, let's predict now several frames in parallel. We predict right now all channels in parallel. Now let's predict all frames in parallel. And what we did, we tried to reduce the frame rate by just stacking. And what we see that in general, you can have not big degradation, a little bit, with a 3x speed up for the inference for your model and also for your training, because sequence became 3x shorter. Okay, so we also looked into ISR. Because we wanted to combine together TTS and speech recognition into one model. So now you just change the input-output from each other. And with that, we show that, yeah, it's working. You can train decoder model. And like DML is working kind of well compared to other standard tachinizers from designed for kind of for speech modeling, but here we're using for speech recognition. And in the end, we try to combine into joint model where you have DML as input, text as output, or text as input and DML as output. And for the joint model, we kind of preserve the TTS quality, but then ISR actually was like hurting. And I would refer that follow-up works from Shinji Lab, where they did 2 papers where they're showing that actually a critical thing was scaling the model size and using the pre-trained text model as initialization, which we didn't do like originally in our paper. So you can train really jointly speech recognition and TTS together, but still they also reporting that as we did, as we saw, and I think other people also saw similar behavior, that you have the issue that it's the scaling. The over the course of the training, the TTS and ISR has different speed in terms of convergence. Okay, so now let's go briefly to SpeakStream. So the boom in interactions and people plugging the LLM to the TTS to have the streaming version. The problem is you need really TTS with low latency, because otherwise you wait the whole sentence, for example, to appear, or the whole paragraph. And exactly with SpeakStream, we did this so that we can run on device with this particular speed. And if you look at the comparison of different open source, not open source, but open source results of some companies and places, we got the best speed. Take this with a bit discount, because it's very hard to compare between the things. It depends where you run, exactly how you run, and it's really very hard to compare latency between different systems in the very fair scenario. So the main thing I can tell you, if you run this on M4, you're going to have kind of under 50 millisecond latency for our TTS model. Okay, so what we do is the following. We do alignment between the text, between the words and spoken words originally in the dataset. So you can do this. There are some open source force aligners. And then we interleave the text and speech, which people doing right now, mainly in the regular grid for the tokens, but we did this in the word space. So now you interleave n-gram, written n-gram with spoken n-gram. And we do this with DML. And that's why your theoretical latency will be exactly how many words you interleave. So with that, we did exploration how many words will affect the performance in terms of the content, but also mean opinion score. And what we found that 5 words, where you have 4 current words plus 1 future word, is enough to preserve the content similar to the full context, but also in mean opinion score, people find with consistency and tone in the generation. And our theoretical latency in the end 5 words, and then if you run on device with MLX on M4, you get 45 millisecond latency. Okay, I will not play example because we have not much time left. And for the streaming vocoder, mainly CNN-based vocoders. And main thing what we did is we make it fully causal, and we introduce upsamplers. So first we upsample the spectrogram, and only after that we're doing real vocoding back to the raw wave. And the final latencies will be like 1 frame. So as soon as I get 1 frame from the TTS, I can generate. So and latency will be 15 milliseconds on M4. Okay, so now let's go to the chip chat. So the main thing is, first of all, we design every component to be separate Python process, where you stream the tokens as soon as they're generated by the model. But in this case, you have additional latency coming from the point of view that every system needs to wait particular number of frames before it starts generation. So in this case, we also optimized this piece and the critical piece and bottleneck, which I was talking about, TTS. So we're now waiting only 5 words to start generation. So that's why kind of having this both in terms of modeling, but also in terms of engineering, how we implemented the stacking of the system and sending right away the piece by piece to the next process, you achieve the low latency, and we got less than 1 second on Mac Studio M2 with MLX. So second piece is we always listen the user. It's 1.5 duplex, what I name it. You always listen the user, and as soon as users stop to talk, you kind of start generation. But if your model generating something and users start to talk, you send interruption to all the system right away to shut down them. And because it's separate processes, you simply can do that in the fast way. So that means that every system stops generation. But the problem is, if you consider some dialogue where I interrupted because I know the answer, in reality, LLM by the time will generate the whole kind of response. And the problem that your player is actually like in this state, but vocoder, TTS, and LLM, they have additional things which they have in the buffers which already generated. And in their states, they are kind of incorrect. The main thing, vocoder and TTS you can reset, but LLM will be incorrectly with the future, tokens which are generated, which you never heard. So this discrepancy leads to the problem of the dialogue state and the fluency of the conversation. So, but because we have the TTS, which generates by interleaving 5 words in written and kind of spoken version, for the chunk of audio, you know approximately where it's located in terms of the written text. That's why you can send from the player, propagated, through the TTS vocoder and then the player itself, the feedback to the LLM to say in which state you actually are right now, because we didn't heard some words. So that's why you can clear the KV cache in LLM. And that's why you have almost precise interruption with the correct LLM state to continue the dialogue. Okay, so with that, I will skip this example. So the key points, kind of the microphone itself, we did implementation in the browser-based with near zero latency and built-in noise cancellation. So that's why you can, really play with the model that TTS is not recognized as with ISR. Filter banks extracted with standard things which people do for the ISR system, 25 milliseconds with 10 milliseconds hop. It's of course running mean and variance for the streaming. For ISR, it's as I said, CTC model with 600 million parameters, 40 milliseconds stride. We use ISR as a VID to detect the pause. We have the training segments, and the key points was also properly resetting the cache, because ISR is not generalizing to the longer durations, and you need to properly handle that. For speaker model, we're right now running just without optimizing the latency, just for the demonstration purposes to have more engaged dialogue. For the LLM, it's 8 expert 7B mixture model. So if you have Mac Studio M2, you can run with this model. This is around 50 billion parameter model total. If you have, a laptop, in this case, you can run smaller models. For example, Llama 3B, we have examples for that. I can run this on my Mac Air with 24 GB memory. So main thing for the bigger model, you need to have bigger GB. So TTS speaks stream with 5-word latency, vocoder with one frame latency, and player doesn't add any latency, and viewer, as I said, the radio. So interruption, we don't vocalize the things which never speaks, but you see this in the text that LLM generated that, so to observe the system, and we properly clear the KV cache. So main thing, we implemented everything into MLX. So if you don't know, MLX is a framework similar to PyTorch, where you have very similar tensor operations, kernels implemented specifically for Apple Silicon. Now they also support the CUDA backend, so now you kind of have unified development of the models to train on the GPU and then convert to to run on Apple Silicon with a shared memory between the CPU and GPU. So we converted all the models. Conversion is actually not complicated. It's almost one-to-one. Just change, import of the libraries. And then this is the latency which we have in the paper, which I benchmarked myself, running the system online and talking with it. So approximately, depending on the generation, it varies, of course, but approximately it's around 1 second. And hopefully you saw in the demo that, you have pretty, natural conversation. And for user, it seems okay latency. So yeah, in conclusion, simple discretization, independent prediction of channels offer alternative way to the tokenization, and you can build with that generative modeling. It's model-free, robust, streamable, multilingual. I think that was one of the key things why we spend a lot of time on that, to go further with the TTS and streaming TTS, and then trying to figure out actually other bottlenecks in the system. And one important thing now, you can see that if you play with the demo, like SRU people played, there is the issue that LLM is actually not very robust to the conversational style of the dialogue, and it can be broken very simply and start to hallucinate weirdly. But this is kind of good baseline for us as researchers, to start to play with it and kind of figure it out what things are missing, what we need to design for conversational AI agents. So in that sense, our kind of main summary from the paper which we did is we designed parts of the cascaded system with a focus on overall system performance, and how we wanted to kind of use this as a baseline, can be compelling alternative for the next generation conversational agents, because speech LLMs are not there yet, in my opinion, in terms of research. So a lot of things we need to do, but it's good to have good baseline to compare with. So yeah, with that, I thank all my collaborators, and part of the things open sourced, part of the models open sourced, not the big ones. We're working on that, and the full code also hopefully will soon open sourced, so I can like stay tuned on my LinkedIn probably to know more and get updates on the open source for the demo, so that you can try on your laptop too. So yeah, with that, I had a bonus, but I don't have time for that. So maybe I will give another talk other time on that. But check out our recent submission where we looked into the text-speech gap between the, like how the speech LLM actually behave when you switch from text-based input to spoken version, and why we have this gap. So we try to reduce this gap, and main outcome, we need to change maybe the loss function, so optimization, and we need to have properly synthetic data or real data to cover domains, so that misalignment between the spoken version and written version disappear in the speech language models. With that, I stop here. Yeah, if there are any questions, we can go with that.
Sure. Thanks a lot, and thanks for the great presentation. I think we have lots of questions, and also ask everyone, if you have any questions, please drop them in the chat or raise your hand. So maybe I could just go ahead and start asking a couple of questions. So first question is that why does the Omni router exhibit better training stability layer specialization compared to the switch transformer? What are your hypotheses about that?
Okay, so one thing is, so specialization, it's better because, okay, we kind of analyze that, right? But my perspective is because you add additional inductive bias and simplified, you can consider, sharing parameters as a regularization, and explicit regularization in our case. So that's why you're restricting your model much, so it's cannot go wildly in terms of specific like selection of the layers. And I think important thing that our model has 36 layers, so we train really deep models for for speech to have a proper speech representation, and that's makes it harder if you don't have this additional inductive bias. For training stability, we still don't know the answer, but I would say we observed them. We tested many different things because of the noisiness of the data, because of the model size. The problem's coming when it's becoming bigger model. So if you train bigger model, then it's becoming more unstable. And I think it's because it's just harder, over-parameterized models, very deep. It's harder to train in general, so optimization just harder. So you can think just it's purely effect of regularization with good properties.
I see. Perfect. Another question is do you think end-to-end the speech system will eventually outperform cascading ones, or maybe a hybrid one?
Okay, I would say we're debating about that in the community. The main argument is that we need to use the speech itself, right? So that's why end-to-end potentially should be better. I mean, theoretically, they should be better. The question how to make it, it's another question. And I think it's open. And we need to have the proper benchmarks to showcase that really speech is used. People there were some papers which were showing that actually we don't use the speech. You just take information purely from text. A lot of things just take, a lot of information from text. We need to be sure that we really use the speech. And unless we have this, good benchmarking, I don't think we can progress well in the community. So I would do call out for better benchmarking development of specific things which we are targeting. But yeah, I mean, theoretically, they should be better. The question about do you want to really to have, interpretability of the system and control over it? That's maybe another consideration. So maybe it will be, some hybrid in the end system where you kind of mix cascaded pieces or, some observability of the system into end-to-end.
I have one question myself. So I have seen that you augment the data with the state action, like emotion and motivation of the speaker. Have you tried using this as a prompt for the TTS to have a specific style or expressiveness, and I wonder how it works?
Okay, people asked me this question before. We didn't try, so okay. I hope I gave you, many thoughts to try, and you have a lot of ideas to try right away with the system in terms of, modify a specific model or use additional information coming from another, places. So as soon as we release that, go ahead and try that. So I will not stop you from that. Please do that.
Perfect. Okay, Mirko, do you want to ask a question?
Yeah, thank you very much for your talk, Tatiana. So my question is about DML, right? So
Yep.
you yourself have noticed that very simple quantization methods work. And also on our side with focal codec, we have seen the same, right? With some kind of quantization methods that are not even learnable, right? So
yeah, I remember
I'm
your paper.
wondering,
Yeah,
and that actually was very surprising to me, right? So why do you think this is happening? Are we learning bad the quantizers, or like simplicity is just enough?
On Spectrum, okay. I saw your focal codec, but okay. There, I don't have intuition. I still puzzled why you see that. For DML, I have kind of intuition because spectrogram is very good featurization. We can read it. I mean, this is interpretable. This is very well, mathematically grounded thing and Fourier transform. So, I mean, from mathematical point of view, with my, background education, I would say this is well-defined thing. And that's why you don't need anything, because you have already all information inside. But I think it's going, in complexity, in some sense, maybe a lot of things actually happening inside the model itself, and information which you need for, language modeling is a bit different from what we actually training the tokenizers itself. Because we weirdly, as I mentioned, right, can like intertwine them, and we cannot, really like expect that the manifold which we learn will be helpful for the modeling. I think in that sense, we have misconnection for which targets we train tokenizer and how we use for the modeling. That's why if you do way simpler thing at the beginning, that's gonna to be better. It's kind of, training the models on the pixels or training models on some latent spaces.
That's interesting. Actually, to me, it seems like, okay, whatever we do with simple quantizer, right, we can potentially learn, but it is not the case, right? So it looks like when we try to learn quantizer with like, I don't know, residual vector quantization, other methods, we are not really learning relevant things, right? So we
Yes, exactly.
Yeah.
Yes. So that's why if you do very simple thing at the beginning, then you're going to
Yeah.
learn this in end-to-end manner in the model. So in that sense, going back to will the models be end-to-end? Yeah, likely, because you're improving your process. The question is, do you have more hallucinations, all these safety issues furthermore? Or if you don't have, likely this should be, the best solution. If you have other things to optimize, maybe not.
Thank you, Tatiana.
Yep.
Okay, so we have a couple of more questions in the chat. I don't know if you have time or...
Yeah, that's fine.
Okay, perfect. So I think we have two questions about augmentation. So what kind of augmentation you use for vocoder, for the ASR or speaker? So what kind of augmentation do you think is necessary?
For speaker, I would refer you to any, SOTA paper model or to our paper itself. But I would say SOTA paper model because we didn't use all augmentation. For speaker model, it's super critical to have augmentation. So any sort of, reverberation noise, additive noise, spec augmentation, whatever you can come up with. Speed perturbation. In terms of ISR, we just use spec augment. So that's a standard thing. We still use even with our kind of a bit noisy data. For TTS, you should not use any noise. You should have very clean data. If you don't have very clean data, this is shown by everyone in the community. You need really to have very clean data to have very good, quality. For vocoder, I think we didn't use any augmentation. You don't need it really because you wanted to reconstruct, right? So in that sense, even reconstruction from the discretized version or the continuous version, it's already a kind of hard task. So yeah, no augmentation for the vocoder.
Perfect. Another question is some of the method, for example, mixture of expert, omnirouter seems generic. Do you see any benefit to them when working under constraint other than low streaming, for example, low data regime, transfer learning, idea specialized type for multimodal?
Can you say this again?
Some of the some of the methods, example, mixture of expert or omnirouter seems generic. Do you see any benefit to them when working under constraint other than low streaming? For example, when you work with low data regime or transfer learning. So what are the benefit of, so do you think that this mixture of expert or omnirouter method that you propose is useful when you work with, for example, low resource data set or something?
Okay. I would say no, because the point of mixture of experts. Okay, so let's do that. If you have some structure of your task where you can say that I could potentially believe in some experts there which should do different job, then yes, it will be helpful. And likely the main thing is, speeding up the active parameters. This is why MOE used, right? Because you're selecting, okay, maybe you can do kind of ensemble of that. Yes, then you could say that this could be helpful for our resource regime, but you don't you don't reduce number of active parameters, you're using all experts. So if you have some structure, I would say that could be helpful. For example, multilingual, people are doing a lot of works on doing a mixture of experts, where expert for every language. So this will be helpful in that sense, so that you have specific component for your dedicated language. And maybe if you train with multilingual regime with your allow resource data for specific language, that's going to solve some problems there.
That's it. So maybe the final question is that how do you control prosody with the system? For end-to-end model, people use RLHF these days. What do you use for the cascaded system to control the prosody?
We didn't use. There was some, I think, NVIDIA work where they were showing that actually you can apply on top of the TTS different RL or classifier guidance, and this even for autoregressive models, kind of classifier-free guidance, and this will improve the consistency of the quality of the speech and consistency of the speaker. So that's potentially can be done. People did some works on that. Yes, it's gonna to work per their papers.
Okay, perfect. I think that we're almost covered all the questions. Thanks a lot. It was a great talk. Thank you everyone for joining. Next week, we will have our last meeting of 2025. We have Daniel from Cohere Lab. So I'm looking forward to meeting you all next week for the last meeting of 2025.